Okay. Right, good afternoon everybody. Welcome to the Society of Popular Astronomy meeting. I'm very pleased to say that we have an excellent speaker here today. It's Morgan Fraser. As you can see, he's going to talk about Gaia, so for those of you who don't know, you'll find out everything about it, but Gaia is referred to as the billion-star surveyor, I believe, of the Milky Way. So basically providing details of the stars and other objects in the Milky Way, the sort of fundamental building blocks, brightnesses, distances, positions, and this sort of thing that we need to do. Lots of different areas of astronomy. So Morgan's an expert in supernovae in particular. Those of us who are old enough remember Hipparchos. The spacecraft rather than the Greek astronomy. Although I see some people at the back. I don't know, I see some people at the back in my room. Anyway, Gaia is the sort of modern version of the Hipparchos spacecraft. So let's welcome Morgan.
Thank you, and thanks for coming along. So I'm, first of all, a confession. I'm not a Milky Way astronomer, and Gaia's main purpose is obviously to map out our own galaxy, the Milky Way. Rather, my own interest is on core-collapse supernovae. So these are bright explosions you get from massive stars at the end of their lives. So at the end of my talk, I'm actually going to come back around to that, and I'm going to talk about how we're using Gaia as a kind of an added bonus of it is that we can find supernovae and other transients in data from Gaia. But first of all, I want to talk about Gaia itself and the main mission, which is to map out the Milky Way. So, without further ado, Gaia. Okay, so first of all, why do we need Gaia? What's the purpose for it? Well, when you look at the sky, you see, if you're lucky, in somewhere dark, so not in central London, you see something that looks a little bit like this. And this is actually a big problem, because every single star in here is just a little unresolved point of light. And you have no idea, is that an intrinsically very, very luminous star, a very bright star that's far away, or is it an intrinsically very, very faint star that happens to be quite close to us? And this is one of the oldest problems in astronomy, this question of distance. In fact, if you look back historically, astronomers have been wrong by, factors of 2, 3, 4, 10 about distances. We're really quite bad at it. So Gaia is built to allow us to put down a measuring stick on the sky and work out how far away things actually are. So how do we do that? Well, you can do it yourself. There is audience participation in this talk, I'm afraid. So if you put out your thumb like this, and you line up your thumb with a distant object, close one eye, and now without moving your thumb, open that eye and close the other one. You see the way your thumb jumps? That's what Gaia does. So this is called parallax. And what's going on here is you're looking at a distant object, your thumb, with respect to a fixed background, the wall or whatever you chose to line it up with, from two slightly different positions, your two eyes. And if you know what those two positions are, you know how far apart your eyes are and where they are, and you can measure that little shift your thumb seems to make. If you can measure that angle, in fact, you can use geometry, trigonometry, to work out how far away it is. So this is the only direct way we have of measuring distances in space, with geometry. And this is what Gaia does. So in the scenario I sketched out, we had our two eyes, we had our thumb, and then we had a distant background. So for Gaia, it's looking at stars from multiple positions around the sun. So Gaia, which is close to the Earth, is going around the sun approximately once a year. And at different positions, it will take an image of a nearby star. And it'll measure that star's position with respect to some background stars, or actually background very distant quasars that don't seem to move. And by measuring this apparent shift in position, it works out the distance to the star. So that's what Gaia does. The interesting thing is when you look at stars in very, very high resolution, this parallax shift isn't the only thing that's going on. So we live in a galaxy that's actually moving, and stars within our galaxy are moving, typically, a few kilometers a second, a few tens of kilometers a second. So actually every star has a proper motion through the Milky Way. Proper motion, the actual physical motion of the star through space. We might also see a star's position seems to wobble if it's got planets around it. So I guess many of you will have heard about how we can find exoplanets. These are planets around other stars. And we find them by looking for the wobble in the star as it moves away from us or towards us. And that's caused by the gravity of the planet tugging that star back and forth. So Gaia will also see this effect. Gaia sees stars actually wobbling in the sky if they've got planets around them. So when you add all these together, your parallax motion, because of us moving around the sun, the proper motion, because of the star moving through the Milky Way, and perhaps even these wobbles caused by planets, when you add all of those together, you find that stars actually trace out very complicated, intricate patterns on the sky. And you can see an example here, one of these sort of like a little bit of a circle and a wobble and a circle and a wobble. So this is really what Gaia measures. And from this, we can work out how far away a star is, where it is, how fast it's moving, and possibly even if it's got planets around it. So, okay. So to make this measurement, we've got to measure the positions of stars on the sky. And we've got to measure this very, very accurately. We already know it's going to be a small effect because when we go out at night and look up at the stars, we don't obviously see things moving back and forth unless they're planets. So we already know we're going to need some really small angular resolution. So this is a protractor. So we have half a circle, and that's divided up into 180 degrees. If we take one of those degrees and zoom in on it, we get, and divide it into 60, we get 60 arc minutes. So there's 60 arc minutes in a degree. And then if we take one of those arc minutes and divide it in 60 again, we get an arc second. So this is 1/60th of 1/60th of 1/360th of a circle. So we're already down to a very, very small angle. To give you some idea, if you take an image from the ground with a telescope with a CCD camera on it, and you're at a good site with good seeing, you can get a kind of resolution, shall we say, of about an arc second. Even this is not good enough for Gaia, and not good enough to actually measure the shifts of these stars. So we have to do better. Gaia measures things not to an arc second, not to a milli-arc second, which is 1,000th of an arc second, but to the micro arc second level. So that's 1,000th of 1,000th of 1/60th of 1/60th of 1/360th of a circle. So this is a really, really small angle. So let's put that in context. We've been able to measure parallaxes for actually coming up on 200 years. So the first measurement was by Bessel in 1831, who measured the parallax of 61 sig to about an arc second. So this is really the only star you can do this from the ground with a photographic plate, or easily with a photographic plate. Before Hipparchus, which was a predecessor satellite to Gaia, you had maybe 100 stars with parallaxes measured, distances through parallax. And the typical resolution here was about 0.1 arc seconds. So this is actually, when we talk about resolution, here we're not talking about how you can separate two objects. We're talking about how precisely you can measure the center of a star, measure the position of a star. So perhaps angular shift would be a better word than resolution here. So yeah, 20th century, most of the time, had about 100 stars to 0.1 arc second. Hipparchus launched at the end of the 1980s, and it measured 100,000 stars to milli-arc second levels. So this is, to micro-arc second levels. So this is already a phenomenal achievement. It gives distances to 100,000 stars in the Milky Way. Gaia will go and measure distances to about 100,000th, a millionth of an arc second, and it will do this for 1 billion stars. So that's an idea of just how we've progressed in the last few decades and centuries. And again, to give you an idea of what the kind of angular precision of Gaia is like, if we were to stand in Chelmsford, and I'll say why Chelmsford in a little bit, and we were to look over to the US coast, if you had somebody in New York and they had a bit of hair like this, and they had a single strand of hair, Gaia would be able to tell one side of the hair from the other. So that's the kind of precision we're getting down to here. So how do we do it? Well, this is the satellite itself. This is a kind of sketch of the structure of it, and this is an artist's impression of what it looks like in space. The whole thing is actually not that big. It's let's see, probably from here to here. That's the width of it, and about that high. It's not huge. That's that kind of central structure, the top hat bit. If you take the brim of the hat, that's a bit bigger, maybe half the size of this lecture theatre. So this brim is a combination of a sun shield, so it's blocking out light from the sun, and on the far side there are solar panels which power the satellite, and then the telescope and detector itself are inside here. So you can see there's two little cutouts, one there and one there. So these are the two eyes of Gaia. So inside each of those you have a mirror, M1 and the second M1. So these are the two primary mirrors of Gaia. Again, not huge. This is about 1.5 meters across. So light will enter in through one of these slits, bounce off one of the mirrors, and it will go down and hit a secondary mirror, and a tertiary mirror, and a fourth mirror, and a fifth mirror, and a sixth mirror, and eventually end up on a camera. So you've got a lot of mirrors in there because, again, this whole thing has to be small and compact and fit inside a satellite. Once the light arrives on our CCD there, on our camera, we can make a measurement of the star's position and its brightness and a whole lot of other parameters. So one interesting thing is, as I said, there's two mirrors in Gaia, two telescope mirrors, and only one camera. Anybody think that's strange? Yes? No? So mixed response on it. So the reason for that is it's actually quite clever. Space is mostly empty. So if you take an image of a star field and you image that on a camera, most of the pixels don't actually get any light from stars. So if you have a second telescope, you can have the light from that second telescope going onto the same camera, and it's actually quite unlikely any stars will overlap. And if you have some clever way of telling which star comes from which telescope, which Gaia does, you can increase your efficiency by a factor of 2. Okay, so this is a picture of Gaia being built. So the whole thing is inside here. This is a sun shield and the solar panels that are in their folded up configuration. So it has to be folded up like this to fit inside the rocket. I don't know what they're doing with it there. I presume that's a drop test. That's a joke. They don't actually do that. Right? They don't tell us if they do. So one of the interesting things about when they build it is this sun shield has to be folded up for launch. So it's got to unfold in space, and you only have one chance for that to happen. And if it doesn't go to plan, you've got a very expensive lump of space junk. So you want to test it unfolding. But it's actually really hard to do that on the ground because this is designed to unfurl in zero gravity. So you can see up here they've got all these kind of pulleys and beams that come down. So they have this contraption that hooks onto it and has counterweights, so it experiences the same forces as if it was unfurling under zero G. So it's just a nice example of one of the sort of fun things you have to think about when you design one of these. And that's the whole thing in its open configuration. Another interesting thing about Gaia is its backbone. So if we just go back a few slides, you can see we've got the mirrors here and the camera, which I'll come on to in a bit, and it's all held together on this kind of thing that looks a bit like a bagel. I don't know. So this is the structure that holds Gaia together. And one of the things when you're making very precise millionth of an arc second measurements of stars is you don't want things to move. So if you have a bit of metal, it'll deform a little bit, and particularly if you're in space where one side of that metal is very cold, maybe you have another end of your metal bar is in the sun's light and it heats up. So it's really important to make sure there's no thermal deformation in Gaia. And that's where this comes in. So this is made out of a material called silicon carbide, which is incredibly rigid. You know, you could put a blowtorch to one end of this and an ice bath to the other, and it will not change length. So again, that's another little example of the sort of technology that's necessary for these missions. Okay, so now I want to come on to probably the most important part of Gaia, which is the camera. So this is what makes it all possible. Once the light comes in, bounces off these mirrors, it ends up down here in a camera. And it's this camera that actually measures the positions of stars, measures how bright they are, and a lot more. It's also the local contribution to Gaia. So remember earlier when I showed you the map and Chelmsford was on it? That's where it's made. And we actually have a small chunk of it to pass around that was kindly given to us by E2V, the company that made it. So this is one of the flight spares from Gaia. So this wasn't used, but it's exactly the same as the ones that are on board. So I'll pass it around, and I would appreciate it if I got it back at the end of the talk. So you'll notice it's not that big. It's about the size of 6 centimeters by 4 centimeters. So in this diagram, which is showing the layout of the camera, what you're looking at there is one of these little cells. So each one of these is a CCD. It's a charge-coupled device that detects light. And if you have a camera phone, an iPhone, what's in that is exactly the same technology as in here. These ones are slightly more expensive, but the principle is exactly the same. And Gaia has 109 of them, all stuck together in an array like this. So one of the interesting things about Gaia is that it's not actually stopping to take pictures. So for Gaia, we want to measure the position of every star we can see in the sky. So we want to cover the entire sky. So we're just continually rotating and sweeping out circles on the sky where we observe. That means we have to, rather than stopping to take images, we have to take a video. So the camera on Gaia, stars actually travel across it like this, or the light from stars travels across it, and we're constantly reading these little CCDs at the same speed as stars drift across. So we get more or less a video of every star in the sky from Gaia. So see the first set of CCDs that stars cross are these ones here called SM1 and SM2. So these are star mappers. And what these little CCDs do is tell you which telescope, which field of view a star comes from. So remember how we got two different telescopes that are imaged onto the same camera? So these first two rows of CCDs allow us to disentangle which telescope saw which star. So then stars pass across these CCDs here called AFs, so astrometric fields. So these are the CCDs, the cameras that actually measure the positions of stars and their brightness. So this will give us where a star is in the sky and how bright it is. And then finally, we have a bunch of stars over here, a bunch of CCDs over here that do something a little bit different. So these CCDs are associated with a spectrograph. So a spectrum is what you get when you pass light through a prism, or when you reflect light off a diffraction grating. And all you're doing is splitting light into its constituent colours. And this is important in astronomy because if you can see what colour of light an object is emitting, if it's emitting more red light, if it's emitting more blue light, you can make an estimate of how hot or cool it is. So cool stars, which are cooler than the sun, so they're maybe 3,000, 4,000 degrees. Cool stars emit more red light. Hot stars, which are 10,000, 20,000 degrees, so much hotter than the sun, they emit more blue light. So we would see more blue light. So these spectrographs here actually allow us to see, for all the stars that we've got positions and distances, how hot they are. We can also, through these CCDs up here, which are another more specialized spectrograph, we can also say something about the chemical composition of these stars. And again, this is because if you have light from a star and you split it into different wavelengths, you'll notice you get less light at very specific wavelengths where it's being absorbed by a particular element. So if you have, imagine I have a box of gas and it's full of hydrogen gas. And if I pass white light through it, I'll find that the hydrogen gas absorbs light at 656 nanometers. And that's a very specific fingerprint to that element. So if I can see where light is absorbed, I can work out what elements are present in a star. So again, that's something we get out of this spectrograph. So yeah, Gaia's mission is to map the Milky Way and to work out the distances to stars, but also we get a whole lot more. We get their temperatures, we get how bright they are, we even get something about what they're made of. Okay, so again, this is the local connections, ETV, who make this CCD that's, still in the audience, good. And you can see a couple of the technicians putting it together there to give you an idea of the sense of scale. Okay, so Gaia itself was obviously first conceived a long time ago. So really, when the predecessor to Gaia, Hipparchus, was operating, people were already thinking, so this is early 1990s, late 1980s, people were already thinking about what was going to come afterwards. So really, it was 2000s and the 2010s when Gaia was built. It was launched in 2013. So the launch itself happened from French Guiana. So this is where the European Space Agency's spaceport is. So the satellite itself was assembled in Toulouse, in France, and parts made all over Europe. It's stuck in the back of one of these carrier aircraft that can accommodate it, and flown over to French Guiana, where it was launched from. The reason why these things launch from French Guiana is, first of all, you're close to the equator, which is energetically more favourable to launch from. Also, you're launching out over the ocean, so if it goes wrong, you're not dropping Gaia on somebody's house, unless they're a fisherman. Okay, so the satellite itself was launched on one of these guys. So this is a Soyuz launcher, which is very reliable and well proven technology, which again is very important if you're launching a irreplaceable satellite. Gaia also has a little thing underneath it, or had a little bit underneath it, called the frigate upper stage, which looks a little bit like this. And this was used to push Gaia into its final orbit. So, where Gaia is an interesting interesting points. I think, some photos of rockets being taken to the launch pad, and that's the launch itself. So yeah, where Gaia is an interesting point. So we typically think of satellites and space telescopes being in orbit around the Earth. So for example, the Hubble Space Telescope is in a fairly low Earth orbit. You can reach it with the space shuttle, or you could reach it with a space shuttle a few years ago. Gaia, on the other hand, is at a point called L2. It's the second Lagrange point. So we've got the Sun over here. It's about 150 million kilometers away from us, the Earth. And if you go 1.5 million kilometers, the opposite direction to the Sun, you find yourself at the L2 point. Now this is a point in space where the Sun-Earth gravity balance each other in such a way that you can have a stable orbit. So Gaia is orbiting around this imaginary point in space, about 1.5 million kilometers from the Earth. There's a few reasons to put it there, mostly to do with ensuring the stability of the spacecraft, that you can make these very precise measurements. It does mean, unfortunately, that it's unreachable, so we couldn't do any repair missions even if we had the space shuttle. Okay, so that's Gaia itself. We're going to measure the positions of 1 billion stars, work out their distances via parallax. We're also going to get temperatures for these stars from their colors, from these spectrographs, and learn a huge amount of information about them. So we get positions for 1 billion stars in the Milky Way, velocities for 1 billion stars in the Milky Way. We get their physical properties. We get a whole lot of information from Gaia. One of the things we don't actually get, unfortunately, are images. So, this is perhaps one of the disappointing things about Gaia, although it was known in advance, that apart from a few images that were taken and sent down to Earth during commissioning, after we just launched, when we're testing out the system, Gaia does not send back any pretty pictures. So it's not like the Hubble Space Telescope. And the reason for this is that we simply cannot send the data to ground fast enough. So the camera on Gaia has 1 billion pixels. It's a gigapixel camera. So this is the largest camera that we know of in space. Possibly somebody has a bigger camera, but they're not telling us. But as I'm sure you know yourself, if you have, even with a smartphone, you fill up the memory card very, very quickly. And if you're trying to email it to somebody and sending it as large attachments, it's very slow. So you can imagine how much worse it is when you have a camera with 1,000 megapixels. So we simply cannot transmit the data to ground. So rather, what we do is on board the satellite, there is a computer that identifies stars in each image, measures their positions, measures their temperature, what their spectra look like, how every single measurement you could possibly think of making from the ground that we would make ourselves on the images, and then it sends down a catalogue of those measurements and chucks away the image. So this is the only way that we can really deal with the volume of data from Gaia. And even with that, we still run into problems where we start scanning through the galactic plane, like the very center of our Milky Way, where stars are most dense. Gaia can get overwhelmed by the number of stars it sees. Okay, so that's kind of mostly the technical side of things. Now I'm going to talk a little bit on the science we're doing with Gaia. First of all, how much of the Milky Way can Gaia see? So I said it's 1 billion stars. So that's our I guess if you only remember one thing from this talk, it's 1 billion pixel camera to look at 1 billion stars for €1 billion. So this is an artist's impression looking down on the Milky Way, and we're around about here. And overplotted on the right, you can see a color map showing where the sources Gaia will see are. And you can see that most of the sources, this little purple region, are actually quite close to the Earth. So this is a natural consequence of a survey that's just looking down to a certain limiting magnitude, a certain faintness. That nearby you're very complete, you see everything. As you move further out, you only see the brightest stars. So actually, we're seeing the dimmest low mass stars in around here, and we're very complete. And then as we move out, we see fewer and fewer stars, and we only see the brightest stars. And then actually, a whole chunk of the Milky Way we won't see at all, just because it's so distant. So again, this billion stars we're going to measure is probably about 1% of the total number of stars in the Milky Way. So there's maybe 100 billion stars, give or take, in our own galaxy. And we see 1% of them. But even with that, we can do a lot of fantastic science. So this is a sort of overview slide showing some of the things we hope to do. So I'll just pick out a couple of them. Let's see. Cepheids. Cepheids and RR Lyrae. Has anyone here observed a Cepheid or an RR Lyrae? I'm guessing there's variable. Right, you must be the variable star mob in the corner. So Gaia can measure distances in our own galaxy. And it can measure distances directly using effectively trigonometry. But when we want to look at distances further out, if you go to even to relatively nearby galaxies, you go to Andromeda, you can't measure parallaxes for individual stars. It's too small a shift even for Gaia to see. Instead, what we do is we use something called standard candles. So a standard candle is simply the idea that you have, say I have a 100-watt light bulb here. And I tell you, this is a 100-watt light bulb, you know that. And I go and stand an unknown distance from you. If you know how bright this 100-watt light bulb truly is, you measure how bright it appears to you, and you can work out how far away it is. So that's a standard candle. And we use classes of stars, such as Cepheids and RR Lyraes, to make this measurement. Cepheids in particular have a very interesting characteristic that they pulsate. And how rapidly they pulsate depends on how intrinsically bright they are. So there's this period luminosity relationship for Cepheids. You measure how bright it's flashing, you can work out how bright it truly is, and then you can work out how far away it is. So we can use these stars as distance markers. The problem is, if we want to use them to measure distances in other galaxies, we have to calibrate them. It's no good these things being candles. They have to be standard candles. We have to know their true distance and their true luminosity relationship. And that's what Gaia does. So Gaia allows us to understand these standard candles nearby, and then we can use those at much greater distances in other galaxies. So really the measurements that Gaia makes underpin this whole distance ladder in the universe, which goes all the way up to Type 1a supernova, which are a very, very bright exploding star, which again follow a standard candle relation of their own, and we can use to measure distances halfway across the universe. But first of all of this distance measurements, standard candles, distance ladder, all of that is underpinned by the distances to the closest stars we see. So that's really where Gaia has an impact. Okay, something else we can do. Dark matter. So this is something. There's probably two massive unknowns in astronomy at the moment that collectively make up an embarrassing fraction of the universe. So we know that ordinary light and matter that we see and interact with actually only makes up a minority of our universe. Most of the matter and energy in the universe is in the form of something called dark energy, which we don't understand, and something called dark matter, which we don't know what it is. So dark matter interacts with ordinary matter, we think, through gravity, but not through light. So it's probably some sort of subatomic particle that you can see its effects on large scales. You can see how it affects the rotation of galaxies, but it's not any form of matter that we've been able to measure in the laboratory or really understand what it is yet. Gaia is going to help us a lot to understand dark matter by actually looking at the motion of stars. So as stars move around in our Milky Way, they're affected by gravity, and they're affected by the gravitational force they see from dark matter. So by mapping out how stars appear to move in our galaxy, we can say something about how the dark matter in our galaxy is distributed. And this is going to be an important clue, not only for understanding what dark matter actually is, but also understanding how it affects galaxies, how it affects the formation of galaxies and the structure of galaxies. Okay, I think that's some of the highlights. How am I fixed with time? Okay. So those are some of the science highlights we're going to be able to do. But probably the single biggest thing Gaia is going to answer for us is on this question of galactic archaeology. And galactic archaeology is an idea that we're trying to understand the history of our own galaxy, the Milky Way, by looking at the stars it contains. So we know that our galaxy has a disk, and we know it's got a disk with probably two components. There's a thin disk in the middle, which has younger stars, young in this case being less than 8 billion years old, and a thick disk which contains a slightly older population with a slightly different average chemical composition. We also know there's a bulge in the center of the Milky Way, and then around all that we have this halo, which is the oldest stars. It doesn't contain many stars, but they're really spread out there. So we want to understand how this structure came to form. So we can answer things like, well, where did our sun form? Where we come from. And we're hoping to understand this with Gaia by being able to map out these different components, see where they are, and hopefully where they come from. So we can start to answer questions like, well, how did the Milky Way grow to its current size? I mean, we know that galaxies grow through mergers, but are we looking at a few big mergers that produce galaxies like this, or is it a series of smaller mergers as the Milky Way steadily eats up small galaxies? So this is a whole new field that the Gaia is really opening up that we can start to understand. Okay, so that's the Gaia mission and perhaps the main science drivers of Gaia. What I'm going to talk about now is a little bit closer to what I work on myself, and I guess it's a sort of add-on bonus mission for Gaia. So one of the things, it's a very common thing in astronomy, is you build a telescope or an instrument or a survey to do one thing, but then when you take all your data, somebody else comes along and says, oh, actually with this data set, I can solve a completely different problem with it. That every time you build a new telescope, there's spin-off benefits of completely unimagined science questions that somebody is going to be able to go and address with your data. And the same applies to Gaia Alerts. So the Gaia Alerts project comes out of the idea that Gaia is scanning the sky over and over. So to make this parallax measurement for stars, we've got to look at the sky, measure a star's position, come back to it a year later, measure the star's position again, come back to it a few months later, measure the star's position again. Since we're constantly looking at the sky, along with the motion of stars, we also see anything that changes. We see anything that gets brighter or fades or changes color. So along with stars, we're also sensitive to transients. This plot here shows some of the sorts of transients that we're interested in and that we can find. So on this x-axis, it's roughly a time scale. So this is roughly how long a given transient lasts. And on this y-axis, it's how bright the transient gets. So the brightest things are at the top. We have things like GRB afterglows. These are gamma ray bursts. So they're associated with core collapse supernova. You have a massive star that collapses down and somehow manages to launch a jet of high energy gamma rays and hard radiation out. They're very bright, but they don't last that long, typically a few days. Other things we find are novae. So some of these are in our own galaxy or in very nearby galaxies, and they're much, much fainter, but last longer. They can last, a few weeks, a few months. And then we find other things like core collapse supernovae, type 1a supernovae. We see quasars, which are somehow connected to the supermassive black holes in the center of galaxies, and maybe tidal disruption events where stars get shredded by black holes. So we find a whole range of transient phenomena that are just waiting for us to pick them out of the Gaia data. So the Gaia Alerts project is being run from Cambridge, and we're taking the data that's sent down to Earth from Gaia HD. We put it into a big database, and we just ask the question, do we see anything in that database that wasn't on that patch of the sky when we looked at it last? So typically we process 40 million observations per day. I think the most things we've seen has been about 200 million sources. So this is when we're going through the center of the Milky Way, when we're looking at the densest region of the sky. And in a few hours to a few days, we process this, we match against our previous catalogue of that bit of the sky, and we find candidate transients. And then all of these transients are released to the community for really anybody to follow up and observe. So this is a sort of schematic of how that goes. We go from the Gaia satellite to ground, to processing in Cambridge, to this whole community. And we have ongoing projects with the Fox Telescope project and LCOGT, who do stuff with schools, with amateur astronomers, and with the professional community to try and observe and classify as many of these transients as possible, and ultimately to understand what they are. So a few science highlights so far. This is the very first transient found from Gaia. We found this at the end of 2014, so this was really in the first Gaia data, and it was a supernova, which I was happy about because that's what I work on. I suppose it might also explain why we found it, because I was only really looking for supernovae, and anything else you just chuck out. So this is an example of what Gaia sees. So the last time the Gaia looked at this bit of the sky, we saw a source there that was about a little bit fainter than 19th magnitude. That was the end of July 2014. When we came back to that position on the sky, around about the end of August, so just a month later, 2014, we saw that source was much, much brighter. And what that source was, when we took images, turned out to be a galaxy that got much, much brighter because a supernova had exploded in it. So this little panel up here shows you an image from the Sloan Sky Survey of this bit of the sky from 10 years ago. You see this smudge in the middle is a galaxy. After Gaia gave us our Gaia alert, we went and observed it again, and we see that next to that galaxy there's another little bright dot, and that's our supernova. Again, if you take this image and subtract it away from this one, you get all you're left with is what's changed, and that's the supernova. So again, you remember earlier I said about how Gaia has this spectrograph on board that splits the light into different colors. So this is useful for transients as well. So this is what the data from the spectrograph looks like. So it's a little bit hard to get your head around at first, but basically what we're looking at in this axis is wavelength, or different colors of light. So this is blue light over here, and this is red light over here. And on this axis is just how much light there is at that given wavelength. The blue and the red lines are the data that we actually got from Gaia. And the black line is a template that we fitted to that allowed us to say this is probably a supernova. And you can see we have these little dips in our spectra that are the fingerprints of particular elements in that supernova. So we can already make a very good guess, even with the Gaia data alone, as to what it actually is. So since then, we found many more supernovae and published these, and are continuing to find supernovae. Another really nice result from the first Gaia data was Gaia 14 AAE. So again, this was one of the early transients we found, and it turned out to be something very different. So in this plot here, again in the main plot, this is brightness. So brighter things are up here, fainter things are down here, and this is time. So this is actually, it's unfortunately obscured, but this is a few years. So what we're looking at is the brightness of a star over several years. You see, it's not really doing anything until Gaia observes it in late 2014. And if we zoom in, we see it's not really doing anything, and it suddenly gets much brighter and then fades away again. So this is a sort of variable star called cataclysmic variable. So it's a white dwarf, so it's a kind of dead small star that's accreting matter from its companion. So it's pulling material off its companion. Every now and then, when it's eaten too much, it burps and has an outburst. And that's what we've caught here. What's interesting about this particular cataclysmic variable is that we don't see any hydrogen in it. So in this plot here, showing, again, this is a spectrum of this cataclysmic variable. So this is a wavelength of light, so this is blue light and red light, and here just how much light we have. And again, we see these what we call emission features associated with helium gas and with silicon, but where we expect to see hydrogen, we don't see anything. So what this tells us is that this cataclysmic variable doesn't contain any hydrogen. And this is already interesting and unusual because hydrogen is the most common element in the universe. Everything's got hydrogen in it. Well, nearly everything. So we observed it a little bit more, and we spotted something even more interesting. And actually, some of you might have noticed it on the last slide. Did anyone? I'll go back. Did anyone spot the interesting thing in the light curve of this guy here? Take a guess?
The dip?
Sorry, the dip? Who said the dip? Correct. So we have dips here. So these are actually real. We see that most of the time, this star is sitting here at 18th magnitude. Every now and then, you'll happen to catch it becoming much fainter. This is about 21st magnitude, so it's getting a factor of 10 dimmer. So this means something's eclipsing it. Something is passing in front of it and blocking out the light. So again, this is incredibly rare. So to get a helium-rich, hydrogen-poor, cataclysmic variable where we're lucky enough that it lines up in such a way that the second star in this binary system blocks out some light every now and then. So we took yet more observations of this. And here we sat on this star for actually not long, just over an hour, taking images every 30 seconds. And again, this is plotting, this is brightness against time, but really only over an hour. And what you see is every 45 minutes, the light you see from the star dips completely, then comes back up, dips again, comes back up. So this is an eclipsing system. And this is really exciting because this is the first known eclipsing helium-rich, hydrogen-free cataclysmic variable, and the first totally eclipsing helium-rich CV. So it actually enables us to understand the system, and from measuring how long these eclipses last, and how faint the star gets, and measuring velocities of gas we see in the system, we can actually solve and work out how massive the little white dwarf in there is, how massive the star it's pulling material from is, and understand things like how this little accretion disk around the star is structured. So this is where this material is pulled off. So this small guy here is pulling material off from its companion and forms a disk around it before it drops onto the star. And obviously the eclipses just come from, as this system rotates, the dips come from certain orientations where the light from the white dwarf is blocked out by its companion. So this was, again, I think we got very lucky with this, that it was in one of the first Gaia alerts, the first transients we found. We published a paper on it, which I was very pleased with the title of it. It was a Total Eclipse of the Heart. That's basically my contribution to the paper. No scientific input, but I come up with titles. And one more recent thing from Gaia alerts that I want to show is, I guess many of you have probably heard about, there was a supernova in Centaurus A a couple of months ago. Has anybody seen it, heard of it, observed it? Observed it. Okay, brilliant. So this is what it looks like. So it's a really spectacular galaxy. So the galaxy is actually in here, and you see these incredible dust lanes from dust in the galaxy that blocks out its light. If you look in radio and X-ray, you see these jets coming out. It's a really spectacular galaxy, and it's very nearby. So this image was taken with the Fox telescope. And you see this little dot in here is a supernova. And Gaia, again, observed this because we're looking at the whole sky over and over. And you can see here a sequence of spectra from Gaia. So again, this is red light and blue light, and these are just a series of spectra taken over time. And you can see the evolution of these lines from different elements that are appearing. And you can also see how most of the light you're seeing is actually in the red. You don't see much blue light. And this is because there's so much dust in the galaxy that it blocks the blue light, so you never see it. So I thought this was a nice fun result to finish up on. So Gaia will continue to operate for the next few years. So it's a 5-year mission, and obviously if things go well, we hope that will be extended. There's not really any limitations. There are limitations on board in terms of how much propellant we have and how well the hardware holds up, but so far it's looking good. The first Gaia catalogue will probably come out around about September, which will have positions for a few million stars and distances for a few million stars. And then over the following years, we'll release more and more catalogues, eventually building up to the final data release, which will be, I guess, early 2020s, where we see it, right, that's it, we're done, there's a billion stars, there's where they all are, we can go home now. But until that comes out, these Gaia alerts are the most immediate science product from Gaia. Now, this is the only thing that's coming out right now. So you can find them all on our website. We'd be very happy for people to observe them and to look at them. And if you find something and it's interesting and you take a nice image, please send it to us. You can see light curves, and you can see spectra and information about how to interpret this. So if you go to gaia.uk/selected Gaia Science Alerts, you can find all our latest discoveries. So I think I'll finish up by just another nice little illustration of the power of Gaia. So this is, can anyone tell me the name of this object? Right, good. I thought it was that, but I thought I should check because... right, so this is the Cat's Eye Nebula, and this is an image from the Hubble Space Telescope, and you see this structure and filaments and tendrils of gas. Here is what Gaia sees. So you remember how I said we don't get any images from Gaia? We just get a catalogue of, I've seen something here, it's so bright, it's at this position. We've taken all the sources that Gaia has seen, And each source that Gaia sees, we've plotted a little blue dot there. So Gaia sees thousands of sources within this nebula. And obviously, all of these sources it sees are not stars; they're little knots of gas. But if you overplot the two, you see that we essentially get all the resolution of the Hubble Space Telescope, but over the entire sky. Okay, so I'll finish up there, and thank you for listening. I'd be very happy to take any questions.
Thanks very much, Morgan. I was massively impressed by that last image, actually, with the cat's eye. Has anybody got any questions for Morgan?
You said that the resolution of Gaia is much better than 1 arc-second, and that in tracking the stars we have to take into account the various elements that make up their motion. Do we also have to take into account the motion of the Sun around the Milky Way, which I've calculated to be about 1 arc-second in 6 months? So if we're going from December to January, then we've moved 1 arc-second.
Yes. So we have to take into account, when you get to this level of precision, you absolutely have to take into account the motion of the Sun through the Milky Way. You have to take into account even relativistic effects like light travel time. So there's an atomic clock on board Gaia, and there's a kind of laser system to measure angles, and there's an awful lot of engineering that goes into doing something that precise.
Will that supernova and Centaurus A still be visible in 2.5 months' time when I'm down in Australia next?
What kind of telescope are you going to have?
300mm at 2.8 telephoto lens with a 1060.
Right.
I'll take lots of pictures of that galaxy.
So do you have filters on it?
No, I'm right in the middle of another hot desert. I don't need any.
No, but I mean, so not for light pollution, I mean just to select out. So the problem with the supernova in Centaurus A is dust extinction. So you're not going to see any light in the bluer parts of the spectrum, but you'll probably still see it in I band or R band. So, well, actually you can go to I think on one of the Gaia web pages there's a light curve of it, and you can see its decline, and you can extrapolate down to see. It's declining. It's post max.
Sorry, this is going to be like a really base question. Sorry, I'm more interested in actually in. So in order you got it in orbit, you said the Lagrange too.
Yeah.
So is it the curve that's keeping it there? I know that obviously I understand the orbit, but how? Because it's constantly falling. I presume you're trying to obviously keep it facing the same place all the time.
So it's. Let's see if I can go back.
Can I go back to the beginning picture?
Here. So it's in orbit around L2. So it doesn't need any propellant to keep it in orbit around there. It needs propellant, so it uses propellant and also reaction wheels, which are like gyroscopes, to point it. So it has to spin every hour and a half to trace out a circle on the sky, and then you're slowly rotating to cover out the whole sky once a month. So that's where the propellant goes. Obviously, there was propellant used as well to get it into position and get it into that orbit. They were very efficient in getting it there, so they used less propellant than they had anticipated. So actually, that means there's plenty of propellant left for the rest of the mission. In terms of is it going to be a limitation in the future? One of the things that could limit Gaia 10 years from now, say if it got renewed, would be running out of propellant. What I suspect might be a problem first is radiation damage to the detectors, the camera on board. So when you're in space, you're above our nice atmosphere, or our annoying atmosphere, depending on how you look at it. So you're susceptible to high energy particles, so cosmic rays, protons, things like that. And every now and then they will smash into your camera and destroy a few pixels in it. So over time, your images get worse, and eventually your camera is just not usable anymore. So that could well be the limit.
Excuse me. I always thought that the Lagrange point though was between the Earth and the Sun. So you had the gravitational pull of the Earth, and then the gravitational pull was like the balancing point. But you've got both the Earth and the Sun pulling the same way.
Yeah. So there's actually several Lagrange points. There is one here. This L1 point is between the Earth and the Sun. There's also points here, so that are 60 degrees, off. So these are so you actually get asteroids kind of clustering around here. You have one the opposite side of the Earth, and then you have one the opposite side of the Sun. So you're right in that this is the L1 is probably the most famous Lagrange point, but yes, you also have these points are gravitationally stable as well.
But isn't the Earth and the Sun both pulling on the satellite the same way though? So why is it balancing?
If you just had a satellite there, it would orbit more slowly than the Earth, so the Earth would go ahead of it in orbit. But the extra gravity of the Earth at that point keeps it alongside the Earth, so the relative configuration stays the same, doesn't it? I think that's
in orbit around the Sun, isn't it?
Yeah, it's orbiting the Sun at the same.
Yeah.
Just the Earth, the spacecraft Earth Sun stays in the same line, doesn't it? Yeah. Question over the far side.
Yes, far side.
Where do other objects in the solar system?
Sorry?
Where is Gaia in relation to other objects in the solar system?
So it's quite close to us. I mean, this is 1% of the Sun-Earth distance. So the closest objects to it are the Earth and the Moon. The other planets are far out there.
If you get hit by an asteroid then?
It would be exceptionally unlucky. That doesn't mean it's not possible, but it's big things, probably not. Small things, you get micrometeorites and dust and things like that could cause damage. But I guess that's a risk anywhere you go in the solar system. So no, there's probably not a major immediate threat from other bodies.
Thank you.
Fingers crossed. There was, I think, a gentleman at the back.
Given the improved accuracy of Gaia, in terms of relative to anything previous, what kind of difference do you think there will be in measurement from current estimates to what Gaia can produce?
So that's a big question, and it depends a lot because Gaia is answering addressing a wide range of science topics. So, for example, I mean, this mapping out dark matter in the Milky Way. You can't do that with Hipparchus. You don't have enough stars. Finding exoplanets. So, for example, when Gaia finds exoplanets by this, its tug on nearby planets, we expect there to be the order of 10,000 exoplanets in the Gaia data. So that's more than Kepler has found. So I think it will be quite revolutionary. What we're going to find and the measurements, what the answers we're going to get, I guess we don't know yet. Otherwise, there wouldn't be. We wouldn't need to build it. So perhaps I'll come back in 5 years and I can give you a better answer to that question. Okay. There was yes.
Yeah. I'm talking about the spacecraft itself now. Like Hipparchus was spinning in order to capture. Is Gaia doing exactly the same?
Yes.
It's rotating, and if so, what's its rotation? How long?
So let's see. I don't know if I have a plot of this, do I? Maybe not. Yeah. So yes, Gaia is rotating. So first of all, it's got these two mirrors. So it's rotating. You can imagine that way, like it's spinning around the brim of the hat. So it sweeps out that every for a star to pass through this field of view, and that field of view is 106 minutes. So a couple of hours, it's done a complete revolution. And then it's also spinning much slower in the other axis as well to cover the entire sky. And that takes roughly 1 month to do the entire sky.
Okay. Thanks very much.
Yes.
I think the Herschel and Planck went out to the L2, didn't they? And the James Webb Space Telescope is going out there as well. I wonder how many can you send out of it? What comes out to Piccadilly Circus? And do your space teams have to liaise with each other to check exactly where they're going to put the telescope?
So, again, I think the answer to that is space is big. So, like the question about asteroids, you can probably put quite a few things there and not have to worry too much about them running into each other. So we should be okay, I hope. Yeah.
What other instrumentation is on board?
So really, this is it. There's, I mean, all the instrumentation on board for astronomy is this camera. So it's taken images to get the positions, and then low-resolution spectra to get colors of stars and chemical composition. There's a couple of other smaller things on board. So, for example, there's star trackers. They're used to orient the spacecraft. There's something called a basic angle monitor, which is a laser system which is used to just measure the position of all the mirrors with respect to each other. But really, it's not like the Hubble Space Telescope where you have multiple instruments that you can select. On Gaia, this is the one instrument.
Electromagnetic sensors?
No, nothing like that. I mean, the star trackers are just small optical cameras. No, so this is really only working in optical light with this camera.
One on the back, I think.
If you look at this spectra you had of essential USA,
Yep.
the peaks, of the various chemical elements don't actually appear to line vertically. Is there something to do with the calibration? That one there.
Here. Yes.
There's actually you can draw two straight lines through that when I looked at it.
Well spotted.
So yeah, you're absolutely right. So if you look at the bottom axis here, this is in wavelength, roughly, but it's not in nanometers or angstroms, it's in pixels. So the idea here is we have our camera, and blue light is imaged onto this pixel at this end of the CCD, and red light is imaged onto that pixel at that end of the CCD. Now, which pixel a given wavelength of light will fall onto will change slightly depending on where your target lies in your field of view. So in the final calibrated Gaia data, these should all line up. But this is because this is unwavelength calibrated data.
I'm just going to take the liberty of asking a question, if that's
sure.
all right.
Yeah.
On your CV light curve, your cataclysmic variable
yeah.
light curve, you had data points from Gaia.
Yeah.
Quite.
So,
like, you know, the within a day, are there days on there?
Yeah, so
is that as they move across the...
So, yeah, that's also well spotted. So, yeah, I said that roughly Gaia will see each position on the sky once a month. However, it depends a lot where on the sky you're looking. Around the ecliptic poles, because of the way we're spinning this way, and we're turning around. You can imagine if I sweep out a circle, there's certain points here and there at the poles that actually have much denser coverage that get imaged more frequently. So there'll be some points in the sky where you actually have a measurement every few hours. So the Gaia scanning law is predictable but slightly complex.
Thanks very much. I don't know about you guys, but I think that was an amazing talk. I think it's an amazing instrument. So let's thank Morgan again.